let me summarize what we did last class. First, mass conservation. Okay. The result was okay. This is 0. This is a continuity equation, right? We derive this one. And here the d rho is density, t is time, d rho over dt is the total derivative. And for incompressible flow, this is continuity equation for incompressible flow. Okay, and last week we also derived the equation of motion. Equation of motion is just Newton's law, F equal ma, right? From that Newton's law, we derive the equation of motion in x direction. And in g direction, w. Gg. Right? This is the equation of motion in 2D fluid problem defined in x and g plane. Then, if we assume the deviatoric shear strain, stress Ij equals 0, and sorry, we have a here we have a Fx, Fg, and Fg equal minus g. That's the body force, gravity force. Then finally we have an Euler equation. P minus g. This is the Euler equation. So for
Rho tau Gc is rho tau Gs.
which one?
Rho tau Gc.
This one? This one?
Left bottom.
This one?
Left.
Here. Sorry, X, yes.
Rho tau G.
Right. ZX, right? Okay, that's the we got an Euler equation. The basic assumption for Euler equation is that fluid is incompressible and inviscid. We don't consider the effect of viscosity and effect of the volume change. This is the result we have last week. Okay, then today let me talk about Bernoulli equation. We start from the Euler equation. If I take the total derivative, the Euler equation give us the Tu u partial x u w equal this is a equation of motion in x direction in Euler equation. This is the equation of motion in g direction. Here I need to talk about in irrotationality condition. If the material, if I take the scalar product like that, this is a vector product about u, this is nabla. This gives us rotation, right? Rotation of particle. In hydrodynamics, we can assume the particle rotation is 0. Okay? Then, in 2D, this means G U minus X W equals 0 in 2D. In 2D. Okay? So, this is named irrotationality condition. Okay. Let's use this condition for the Euler equation. Look at the equation, this one. This is same to this one. So instead of this, we can use partial W, partial X, right? And also, and here, we can use partial G, partial U, right? Then let me see what happened here. The both equation can be changed, its form. U plus one over two U square plus 1 over 2 W square equal minus and second one we got this equation. Okay, can you follow? Something wrong? Ah, sorry, I missed G. Here I need to have G. Actually, here let me introduce the velocity potential. When the where is it? Sorry. When here the pi is velocity potential, its name, velocity potential. Potential. Okay, so that this kind of velocity potential exists only when the rotationality, irrotational condition is satisfied. Okay, so if we use this equation in our the above equation over here, so we can write down that Euler equation in terms of velocity potential. Okay, then we're gonna have a two equation, partial minus plus 1 over 2 square plus square plus P something, sorry, there is something wrong, equal sorry, there is something wrong. Okay, sorry, I'm sorry. Let's rewrite the equation, this one again. I'm gonna take the rewrite that one, then T minus T sure U, right, plus another U, each X X, oh sure, what 2 is Q, W is Q. This is quite a long equation. And second one, minus G plus same thing G and same thing minus 1 over low minus G, right? So here we can rearrange the equation. P rho equals 0. Minus 0 G. Here we can integrate both equation about the x, about the g, right? We can integrate equation, two equations. First, I can integrate the first equation about x. I can integrate second equation about g. That's very simple process. Then we will have a t pi plus 1 over 2 u square w square p over rho equal, there are going to be some constant, and that constant should be about x, right here, C1 x n times t. And second equation, this is about t, same thing, minus rho g plus the other constant C2 xt. Okay? So if you look at the both equation, the left hand side are same, right? Then how about the right hand side? Right hand side should be same, right? Then look at here. Here the C1 is a function of x and t. C2 is a function of G and t, right? G and t. So if you examine both equations, C1 and C2 should be only function of t, because both in both equations right hand side should be same. So from two equations I can get one equation minus t plus u square w square plus p rho plus gg equal only constant should be only function of time, not a function of x and g. And here we can get rid of this c, that constant. There are just several ways to get rid of that. One is this constant can be included into the potential function. Okay? So this is a Bernoulli equation. And in pure potential term, P rho plus 1 over 2 Gg equals 0. This is named Bernoulli equation. What's the power of Bernoulli equation? We had two equation of motion in x and g direction, but here now we have only one equation, right? The equation doesn't depend on the direction. So that name is Bernoulli equation. To derive the Bernoulli equation, we used a lot of assumption, right? Incompressible, irrotational, and inviscid, and low is uniform. Okay. Actually, I didn't mention about this one, low is uniform. To integrate in x and g direction, this assumption should be given. Okay, so I think I derived all the fundamental equation of fluid mechanics to get into the wave mechanics. Now let me talk about our main topic. Main topic is small amplitude water wave theory. Wave theory. Okay. Let's say we have a coordinate system G and X, and this is bottom of our C bottom. Okay, and there are going to be some wave wave height is h, wavelength L is a wavelength. Okay, this is our domain. We need to solve. And actually, in most of physical problem, in mechanical problem, in solid and fluid, we need to solve carbon equation. Okay? And also, based on boundary condition. So, actually our problem consists of carbon equation and boundary condition. So now let's see what's the carbon equation for this small amplitude water wave theory. First, carbon equation. In this water wave theory, carbon equation is continuity equation. This is 0. In x from 0 to L, and G is minus H2 surface. This is surface. This is surface function. It's a function of x, it's a space, and time t. This is just 2D problem defined in x and g plane.
Is that one or that?
Huh? Which one? This is 1. Sorry, this is L. Okay, so when the velocity potential exists, velocity potential, the velocity vector going to be like this. Let's use this definition in the continuity equation. Then we are going to have a Laplace equation. 0. This is a carbon equation of our problem, water wave problem. So we have carbonication in equal 0. Okay? This means x x square plus g equal 0. Same thing. We need this Laplace equation. Laplace equation. Okay? Laplace equation is carbon equation. And in small amplitude water wave theory, the basic assumption, this water wave theory, small amplitude is a basic assumption. Amplitude. This means our surface function is very small. Okay? Here the x-axis is the line when the surface is zero surface. Okay? And u, w, p is small. At surface. Because the wave amplitude is very small, it means the wave speed, the speed of the fluid at that surface is very small, okay, and pressure is also small. Here, I can assume our pressure is 0 at air. So that's the basic assumption for small amplitude water wave theory. Okay, this is a carbon equation. So then let me talk about boundary condition. So this carbon equation should be satisfied in the old domain. All the domain here we define. And second boundary condition, bottom boundary condition. I like to say just BC, bottom boundary condition. Boundary condition. Okay. This is the bottom here. At the bottom, there are going to be no velocity normal to this bottom surface, right? So W equal 0 on G equal minus H. W is can be expressed by the potential is 0, right? This is a bottom boundary condition. So this is at this is W. W equals 0 at the bottom. This is a bottom boundary condition, like say BBC. Okay? Bottom boundary condition. And third, at the free surface here. At the free surface, velocity normal to the velocity in g direction will be same to the velocity of the surface, right? So, and this is named kinematic free surface boundary condition. Okay? On g equals 0. So here we need to have a boundary condition that the KFSBC, wrong name, KFSBC, that's the second boundary condition, and fourth, at the free surface, the Bernoulli equation should be satisfied. What was the Bernoulli equation? Bernoulli equation was plus GG equals 0. Here, in small amplitude theory, the velocity is almost 0 and pressure is 0. So we have only two terms. Now we have only two terms. Minus T GG equals 0 on G equals 0. This is named dynamic free surface boundary condition. Dynamic free surface boundary condition. So, dynamic free surface boundary condition. Okay? So we have a we have a carbon equation in the main body, fluid body, and we have a we have a carbon equation for the main body of the fluid. We have a boundary condition at the bottom, one boundary condition. At the top, we have two boundary conditions. How about the left hand side and right hand side? They're going to be a boundary condition too, right? This was a 4, 5. Periodic lateral boundary condition. It means the potential function should be periodic. X plus L T in space, and this potential function is periodic. So T, sorry, it's not L, T, in time. Okay? Now look at this picture here. This is a sine function, just right? We just assume the surface shape is sine or cosine. So we have this is just one cut of the sine or cosine function. This will be a periodic about the time and about the space. That's the boundary condition. Periodic lateral boundary condition. This should be satisfied here and here. Right? So we have one governing equation and lot of boundary condition. Right? Now we need to solve. This is very challenging. Too many equations? Why? Okay, I want to show you the how to solve. Okay, it's a really big work to show all the derivation, right? So first step to solve is in this here the unknown is the potential function, right? That's a scalar. So if we calculate the potential function, that's it. Everything can be automatically obtained. Separation of variable. So this separation of variable technique have been used for many partial differential equations. This is a very common technique, right? So we just assume our potential function is actually it's a function of space. I mean the function of x and g and function of time, like that. So we assume this potential function consists of function of x multiply function of g multiply function of t only, right? Here the x, big X is only function of x, big G is only function of g, t is only function of t. Okay? So here I'm going to use the periodic lateral boundary condition in time. Okay? Then we can assume that time function t can be a sine function, sine sigma t, right? We can assume the time function is periodic about the time, so we can use the sine function, or we can use also cosine function. And here sigma equal 2 pi over L. Sigma is a frequency, wave frequency, L, sorry, this is a T. T is a period, wave period. Okay? So, then our potential function become x, g, multiply sine sigma t. Right? And this is our governing equation. Laplace equation. Let's put this function into the governing equation. Governing equation is that x squared plus g squared equals 0. Then we are going to have an equation. This is a very simple process. You can do it by yourself. dx squared d squared x plus equal 0. You're gonna have this equation. Look at this equation. Here the first term is only function of x. Second term is only function of g. Right? So, to make some of these two terms become 0, there is only one condition. This become a sum constant. For example, minus k squared. This become a constant k squared. That's the only condition which satisfy the sum of that is 0. Then we're going to have two equations. Equation about the x equal minus k squared. Equation about g k squared, right? We have two equations. First equation is only about the x. Second equation is only about. So originally we had a partial differential equation, which is the equation was about x, y, x, g, and t. Now we have only two. First one is only this. It's not a partial differential equation. Now we had two separated the ordinary differential equation. So now you can solve, right? Each one. You can solve each one. So if you solve the equation which satisfy the periodic boundary condition in space, we're going to have a solution. X is A cosine kx plus B sine kx. Okay, G equal C exponential kg plus D exponential minus kg. Right? This is our solution. Look at this. X. This equation satisfies the periodic lateral boundary condition in space, right? Periodic lateral boundary condition in space. Because here we have a kx. This is sine and cosine function. Both are periodic function about the x, right? And k is L 2 pi over L. L is a wavelength. K is named the wave number. So do you remember? Sigma was 2 pi t. This is a period. Wave period, wave frequency. You should know about these four characters: wave number, wavelength, period, and frequency. Okay? Let me talk about that a little bit. The ocean wave, let's say there are some ocean wave. This is an ocean wave at a fixed time. At time is some specific time. You can take a picture of the ocean wave. I mean, you fix the time and you got this shape, right? Then this will give you wavelength. Okay? This is with wavelength. And second, just fix some position. X equal x0. And look at how varied at this point, how this is let's say this is a time equal t1, and this is a time equal t2. If we fix the position at this point, you're gonna have at that point you're gonna have a wave, and this is at this point, this is a wave about the time. Okay, something like that. This is a period. I mean, if you fix the time you can get a wavelength. If you fix the position, you can get a frequency and period. Okay. Yeah. Can you understand? Little bit confused? So, wave is moving, but it's a sine shape. Okay, so let me continue. So, our solution about the x is a cosine kx plus b sine x sine kx and g equals c e kg plus d e minus kg, right? Then our potential will be this term multiply. So a cosine kx plus b sine kx and g term e kg. Here I should have c e kg plus d e minus kg and sine sigma t, right? So here we have a constant a, b, c, d, right? We need to determine that constant. How? By using the boundary condition. We have a lot of boundary condition. Okay. Here, first of all, let's just consider this one first. So I don't want to consider this one. Okay. I want to consider this term later. Then our potential will just simple form like that. So we need to calculate the constant A, C, D. So here, let's use bottom boundary condition, BBC. BBC is W equals 0 on G is minus H. Minus H, the elevation at the sea bottom. And W equal minus partial potential partial G equal 0. On G equal minus H. So just put this potential into here. And then you can get the potential pi our potential becomes simpler. And pi equal g. This is the other constant, cosine kx, cosecant k h plus g sine sigma t. Here I have h. This is another cosine, hyperbolic cosine, okay? So if you apply the bottom boundary condition, we got this equation. Then let's apply dynamic free surface boundary condition. This means this is your Euler equation, right? T plus Gz equal 0 on 0. Okay? Then from here you can get a potential K E H G sigma KH H K H plus G cosine KX sine sigma T. Equation look complex. Actually, applying the boundary condition is just, it's not a big deal. You can do it by yourself. And from this potential function, we can calculate surface function 2 over h cosine kx cosine sigma t. Oh, sorry, this is wrong. This should be G. So you got an equation, you got a solution. This is one of the solution. Okay, which satisfy the governing equation and all the boundary condition, right? But we have one more boundary condition here. So it's not all the boundary condition. So this equation make satisfy all the boundary conditions. We need to consider one more. The kinematic free surface boundary condition. Okay. This was G. Velocity in W direction is the same to the velocity of the free surface on G equals 0. So if we apply this condition, so here put this potential and surface function into here, you're going to have very important relation. Sigma square is a frequency square. Gk, k is a wave number. Hyperbolic tangent, kh. You are going to have this equation. The name of equation is a dispersion relation. Okay, look at the equation. G is given, right? And sigma is a frequency. 2 pi over t. And k is a wave number. 2 pi L. So this equation gives us relationship between the frequency, it's about time, and wave number, it's about space, and h, water depth. Okay? This equation gives us the relationship among the also wavelength, period, and water depth. It's named dispersion equation. So, in our solution here, the K and sigma should satisfy that relation, dispersion relationship. Okay? So, if you look at this, if the K and H is given, we can calculate sigma. If H and sigma is given, we can calculate K. Okay? So, our first solution for the surface, it's x, function of x and t, was h over t cosine kx cosine sigma t. Okay? This is x, t. Let's look at the equation, this one. When the kx, cosine kx, so shape is like that. Here, this is when the kx equal pi over 2. Over 2 here, kx equal 3 pi over 2. Right? In these 2 points, always 0. The wave shape is always 0. Right? As time change, wave shape change like that. Okay? So this wave vibrate. This point, there is no change. Always the surface point position is 0, and also like change like that. This is when sigma t. This is when sigma t equal sigma t equals 0, when sigma t equal pi, right? Something like that. So, look at this. The wave doesn't move, right? Just vibrate in same position. So, name of this wave is a standing wave. Standing wave. Okay, so we got one of the solution for water wave. It's named standing wave. Okay, it's a standing. Here x equals 0. Here x equals L. Do you remember we didn't consider one more possible solution? The sine term, right? So let's say this is solution 1. Solution 1. There are going to be one more solution. So there are going to be one more solution. That's going to be another standing wave. Another solution is that this one, h over 2 sigma g cosine h k h cosine h k h plus g and sine kx cosine sigma t. The form of the solution is very similar. Only difference is sine and cosine, right? Minus h sine kx sine sigma t. This is another standing wave. Okay, let's say this is solution 2. Okay? Yeah. Only difference is over there, the cosine, cosine, here sine and sine. This is the same, has the same property, but different shape, right? So this solution also satisfies the governing condition, governing equation, and all the boundary conditions, and also this equation satisfies the dispersion relation. Okay? But here we can think the equation 1 minus equation 2. Can it be a solution? That can be also a solution, right? That can be also a solution. The position of both will be a solution. If you sum both, that's going to be a solution. If you subtract or multiply something and sum, then if you do this process, we're going to have another solution, G sigma hyperbolic cosine kh hyperbolic cosine h plus g sine kx minus sigma t. Okay, and h cosine kx minus sigma t. Okay. If we subtract both two solutions, then this is not a standing wave anymore. Because two standing wave has a different phase about the space and about the time. Due to the phase difference, this make a progressive wave. Okay, progressive wave means wave is moving like this. As time goes, wave is moving. Okay, here the original, this is a time, let's say t1, this is time is a t2, and this is x, space x. So let's look at these 2 points. Then this point, this is x1, this point x2. We have the same elevation, even the position and time is different. So t x1 t1 equal x2 t2, right? And here this equation. In this equation, let's put the x1 t1 x2 t2 over that equation. Then k x1 minus sigma t1 should be same to the k x2 minus sigma t2, right? Then this will give us sigma k equal x2 minus x1 t2, x2 minus x1 t2 minus t1. Watch this. Watch this. Huh? This is a wave speed. This is a c and wave speed. Okay? So now you can calculate the wave speed. It's a ratio between the wave number and wave frequency. This is wave speed. Yeah.
Another solution.
This one?
Standing wave.
Yeah.
The potential, velocity potential. The t term should be sine sigma t.
This one? Where? Huh?
About the velocity potential.
The velocity potential here. Why?
Because we start with t, large t is.
Yeah, but it's that, yeah, sine and cosine function are both are periodic. It doesn't matter. Okay?
And the same goes for the.
So first time we assumed our periodic function about the time is sine. But even you are using the cosine, it's no difference. Sine and cosine both are same periodic function, only difference is page, right? So just drive by yourself, then you're gonna know the no difference. Okay, so now we calculate the C. So C equal K sigma. Huh? What's the sigma and K? Sigma is T 2 pi is K 2 pi over L, right? This will give you L T over L. T over L. Okay? Sorry, there is something wrong. Sorry. This was totally wrong. Sorry. K sigma. This is K sigma. K sigma 2 pi L 2 pi T equal T over L. So L is length, T is time. So this unit is correct. Okay. So now you know how to calculate the wave speed. And we don't have much time, but let me talk about for final one, dispersion relationship. Okay. Relation. Okay. This was a sigma square gk tangent, hyperbolic tangent kh, right? With sigma equal 2 pi over t, k equal 2 pi over l, right? Here we have some unfamiliar function, hyperbolic tangent kh, right? You know how to plot? So the function looks like that. I'm gonna draw, here. This is KH 1.0. So tangent, hyperbolic tangent KH. This will be like function like that. As the KH become bigger and bigger, that function goes to the 1 asymptotically. And this is let's say this is a y equal kh. Okay, in this region. So pi over 10. When the kh is smaller than pi over 10, hyperbolic tangent kh is just kh. And in this region, hyperbolic tangent kh is similar to 1.0, right? Because the k is 2 pi over L, this is a h over L is smaller than 1 over 12 here. H over L is bigger than 2. Okay? So let's think about these two cases. When H over L is 1 over 20, when the H over L is more than 2. Okay? When H is water depth, L is wavelength, is 1 over 20. We are saying this is shallow water. Shallow water is defined by ratio between water depth and wavelength. If water depth is 1 kilometer, even if water depth is 1 kilometer, if the wavelength is maybe 20 kilometer, they're going to be shallow water. Okay? So this is shallow earth. In shallow earth case, we can use this relationship. Then sigma square is G K square H. Okay? And C is a K sigma will be a root GH. Okay? So in shallow water case, the wave speed is only function of water depth. Okay? When the water depth is very deep, for deep water, our wave speed going to be faster. And when H over L is more than 2, this is a deep water case. In this case, G square, sigma square is a GK. Okay? For deep water, when in deep water, let's say L equal L0. So L means the L0 is a wavelength in deep water.